Good evening, everyone. A pleasant evening to everyone here. Thank you for taking time from your busy schedules to spend this evening with us. I, Shikha, along with my friend Bhavika, will be your host for the today's event. If you are here, let us know by putting a hi in the chat box. Like, I want the highs in the chat box so that everyone is here. Yeah. It's great. Like you all are here. Okay, that's wonderful. So you all are excited about the fantastic workshop, the satellite designing. If yes, then drop yes in the chat box. Yeah, like everyone is excited about the workshop, right? So just I want yes in the chat box. Everyone. Yeah, wow, that's great. Now, I would like to invite our President, Ms. Sakshi Nagaich, to introduce our chapter. Sakshi?
Uh, Hello everyone. Am I audible?
Yeah, Sakshi, you are audible.
Okay, so good evening everyone. Uh, my name is Sakshi Nagar. Student for the Exploration and Development of Space is an international student-based organization whose purpose is to promote space exploration and development through educational and engineering projects. SEDS is a development of future leaders and contributors in the expanding space university. Seds Nebula of VIT Bhopal is a subchapter of SEDS India. SEDS India is a governing body of SEDS in India was established in 2004 with its headquarters at VIT Law. Talking more about the division of working. So we have three working divisions, namely core, outreach, and projects. One of the chapters one of the chapter's main objective is to generate interest by educating people about the infinite possibilities of space, supporting a network of interested students. So, under the banner of COLE, we usually organize workshops and webinars within our university, such as this one. Coming to the outreach, as the name suggests, it includes visiting government schools and NGOs, motivating them for space-related activities to the expert lectures and presentations. Our effort will spread awareness regarding space program exploration and basic phenomena of physics. Last but not the least, our most exciting, the project team, tries to explore various possibilities in the field of space and turn them into pursuable projects and research. The team are also recognized for the projects and the research work they will take up individually or as a part of reputed research institute in our country. At Seds Nebula, our project team usually keep themselves involved in various space-related projects such as rover designing, CanSat, and many more. This is all about our chapter. So, as I got a lot of questions like how we can join this chapter, answering your many queries and emails, we will share the details of recruitment process soon after the World Space Week celebration, through which you can be a part of exciting chapter. So stay tuned for that. Now I would like to hand it over to our host. Thank you, Shikha.
Thank you so much, Sakshi, for introduction about our chapter. So being with the exploring space has inspired millions of people. So with the same motive, our guest organization ORION Space was established in 2017 in Nepal to promote the space education and build capacity among the engineers, students to work in the field of space technology. The primary objective of ORION Space is to work in the development of satellites. Currently, they are involved in the development of Nepal PQ-1, which is the Nepal's first picosatellite. Now, the session will be continued by my friend, Ms. Bhavika. Thank you.
Thank you, Shikha. Our today's guest is Mr. Rishi Sharma, who is currently working as research and development engineer at ORION Space. He is involved in projects such as reaction wheel-based CubeSats, ADCS, automatic weather station, and prototype of GO-2 telescope. His research interests are applications of differential geometry in control systems, general theory of relativity, and attitude estimation. On that note, I would like Mr. Rishabh to begin with the event.
Hello, can you hear me?
Yes, sir, we can hear you.
Uh, Thank you, Seds Nebula, for inviting us in this talk, and thank you for such a nice introduction. My name is, as already it has been said, my name is Rishabh, and I'm working as research and development engineer at Orion Space. I got involved in Orion Space as my final year as engineering student, and I recently completed my bachelor's in electronics and communication engineering. uh, I was involved in Orion Space as I did my final year project in attitude determination and control system for CubeSat applications, and that is the topic that I'm going to talk about now. And as a side note, I'd also like to uh, give a preface that if any of us here are interested in mathematical modeling and interested in both the physics and space technology, then I think the attitude determination is the best subsystem of satellite that that you love doing, because there we need to do mathematical modeling, simulations, and do electronics and all sort of things like physics, engineering, electronics, coding. All things come together in this attitude control system, and that is the topic that we are going to cover now. Um, I'm going to share my screen. Can you see my screen?
Yes, sir, we can see.
Before continuing with the attitude determination and control system, I like to mention that Thanosat-1, that is the small satellite built at Orion Space, is about to get launched at on January 2022, and it is already on its way. And it is very proud moment for us, because it is not only the fact that it is second satellite launched by Nepal, but it is the first satellite that is completely built and about to be launched from Nepal. And this is the satellite, and I think most of us are already aware about this fact, but if any of us are not, I'd like to mention that when we talk about the satellites, we are not always talking about the big satellites that we see in TVs and internet. The satellite can range from the size of house to the size of Rubik's cube, and the reason behind that is because uh, the developing countries cannot dedicate their finance to the development of larger satellites. So, in order to do so, the concept of small satellites was introduced, so that even a university can provide the money to develop, launch, and operate the satellites. And that that is the class of satellite that we are working in Orion Space. And those satellites goes by the name of CubeSats and Picosats. CubeSats are those satellites whose lengths are 10 centimeter by 10 centimeter by 10 centimeter. So it is basically a cube of 10 centimeter uh, dimension, and those sort of satellites that have a dimension of 10 centimeter cube is known as one unit satellite. So if you want to build a larger satellite, you can extend the satellite by joining another one U part, and it becomes 2U satellite. Similarly, there are also another class of satellites known as pocket satellites, and those are the ones which have the dimension of 5 centimeter cube. And I like to mention that the size of picosatellites that you are going to build depends upon the mission design that you have put inside the satellite. So if you have heavy equipments and larger sensors, then of course the 5 centimeter cube of space won't be enough for you to hold the satellite. So it completely depends upon the type of mission that you are going to do. But the part that we are talking about is not actually about the introduction to satellite, but about a specific type of subsystem that is present in the satellite, and that is known as the attitude control system. So before we actually go into the attitude control system, I like to develop the scenario so that it will give us the intuitive feeling of the problem statement that we are talking about. So let us suppose that, oh yeah, and while along this lecture, we need not constrain ourselves to the pocket sat, because the theory and the concept that we are going to talk about is equally applicable to large and small satellites. But if there are any distinctions to be made, then I'll mention it while I'm describing the topic. So first of all, let us imagine that we have a satellite and it is orbiting around the Earth. And this image I took is that of the Hubble Space Telescope. So this satellite itself is a large telescope. And let us assume that the Hubble Space Telescope is supposed to take the image of a star known as A. But we can already see that from the place where it is now in the orbit, it cannot point its telescope towards the star A, because it is aligned on the direction that is not towards the star A. So this is the problem statement that we face when we build the satellite that needs pointing applications. And it need not be a telescope, it can be camera. Let's say we have a satellite that is fitted with a camera and we are supposed to take the images of India. Then when it is on the orbit, and if our camera is pointing towards the black void space, then we are not able to take the image of India from the orbit, because our camera is not pointing toward the India. So in such cases, what we need to do is that we need to rotate our satellite such that the sensor that is fitted in the satellite points toward the direction that we want it to face. So in our scenario, uh, let us suppose the direction that our Hubble Space Telescope is facing right now is B. So the direction that we want it to face is A. So what we need to do is that we need to rotate our telescope so that the telescopes our satellite shows that the telescope is pointing toward the star. And this is the type of problem that we are talking about when we talk about attitude control system. So let us talk about the name itself. It seems funny because the word attitude coming with the word satellite, and please don't get confused upon this fact, because the word orientation is often replaced by the word attitude when it comes to the space technology. So whenever we talk about the attitude in space technology, we are talking about the orientation of the satellite with respect to the Earth. So the term is attitude control system. Attitude control system. Uh, we saw that the word attitude means orientation. So we are talking about orientation control system. And as we can see from this problem statement, our orientation of the satellite is towards B, but we want our orientation to be towards A. So in order to do so, we need to point our satellite from B to A. And that sort of problem, will we take the present value of our satellite to the desired value, is known by the name of control system. So the attitude control system means the subsystem of satellite that deals with pointing the satellite toward the direction that we want it to point. So now we have formulated our problem statement, and based on the content of today's talk is, if we go in detail, it is actually very vast, and mathematically also it is very rigorous. So the flow of talk that we have designed for today is what sort of technologies are used to rotate the satellite in its orbit. So before going on, it is very important to
Excuse
mention.
me,
Yeah, please.
sorry to interrupt, but
Yeah.
your voice is a little bit low. It's not
Okay.
stable.
Is it? Can you hear me now?
Yeah,
Is it?
yeah.
Yeah. Is it good now?
Yes, it's good now. It's fine. Thank you so
Thank you.
much.
And I like to mention that as I have already talked about it before, the satellite subsystem satellite might not always be equipped with telescope. It might have camera or it might have unidirectional antenna. The type of antenna which needs to face towards it is its receiver, because when we use our phone, we need not worry about where the antenna of our phone is pointing towards, because the type of antenna it uses is known as omnidirectional antenna. It captures the electromagnetic wave from any direction. But if our satellite was equipped with unidirectional antenna, then we must make sure that the satellite is pointing towards, let's say, India, to make sure that the ground station of India is taking the signals that are emitted by the satellite. So in such scenarios also we need the pointing applications, and so we need the attitude control system. Similarly, we need attitude control system in interplanetary travel. Let's say this is Earth and this is Moon where we are supposed to travel, and let's assume that it is the trajectory that our spacecraft is supposed to follow. So in order to do so, we must make sure that our spacecraft is going toward the direction that was already pre-planned. If our spacecraft is directed toward this direction, then the members on board will never reach the moon. So attitude control system is also very important in such scenarios. So, and now that we have discussed the problem, and I think the this microphone that I'm using has trouble. So if my voice goes low again, please let me know again so that I can know.
Yeah, sure.
And now that we have discussed the problem statement, now we'll go to the actual problem, that is how do we rotate the satellite, because satellites are very large bodies as well as very small bodies. So if we are talking about big satellites like Hubble Space Telescopes or International Space Station, then it is reasonable to assume that there might be large attitude control system so that it will move the satellite toward the required direction. But we have also already discussed that satellite can be as small as 10 centimeter cubes. So attitude control systems are equally used in those small satellites as it is used in large satellites. So it is very interesting problem. So the technology that we are talking about must fit into a small scenario, and also it must provide enough power to move the larger satellites. So the first type of technique that we will use is known as direct torque technique. And I think the term direct torque technique is not actually the term used in literature. I have used this term just to classify the type by which we move the satellite. So uh, it will be better if we go into the what the direct torque means instead of pondering upon the term itself. So let us suppose that it is our Q satellite, and and also let us suppose that this green arrow denotes the direction of the camera, and currently our camera is facing toward this direction. And let us also suppose that we want our camera to face towards this direction. So most reasonable thing to do in this scenario is that if we assume that the center of mass of the satellite is this, then we can provide torque from this direction so that our satellite will rotate in counterclock direction, and the green arrow, that is the present orientation of our camera, will match with the expected direction of our camera, so that our camera will face toward the direction that we want to face. This is the direct torque method. You actually apply torque to the satellite so that it rotates. But there is one huge problem. That is, let us imagine a man applying torque to this point on this vehicle. and he is using this rod to apply the torque. And it is common experience that in order to apply torque, we always push against something in our daily experience. Let us suppose if this were wall and if this was a person pushing the wall, then his legs are pushing against the floor in order to provide enough force to the wall. And in this case also his legs are pushing against the ground so that he can pull this lever more strongly. But it is very well known fact that there is nothing in the space to push against, because the space is void and it is in the vicinity of our satellite. It is only our satellite that exists in space. So in order to provide the torque that we need to direct our satellite to the required direction, we do not have any point to push against. And that is the real problem. So that problem is solved by taking advantage the Newton's third law of motion. That is what we do is, instead of imagining that we need to provide torque to our satellite from external direction, we can equally assume that we can equally do something creative. That is, we can eject some high speed particle from the satellite in this direction. And we know that the third law of of motion of the Newton says that for every action there is equal and opposite reaction. So if we eject high speed particles from this point, our satellite will experience opposite force in this direction. So the force that we imagine to be applied externally, let's say this was our satellite and this was our man, and his legs should be pushed against some uh, firm ground in order to apply torque. So this was the problem. So we eliminate this man and we put some sort of nozzle layer which emits particles in very high speed, so that opposite force is applied in this direction, which works as if the man was pulling the lever. So in this when it comes to the use of propellant in attitude control system of satellites, there is always involvement of some sort of propellant. So this example can directly be related with how the rocket works. Let's say this is the rocket and this is the nozzle, and when the fuel is burned uh, above the nozzle, the high speed combustion happens and the opposite force is experienced by the rocket, which is lifted off the ground. In the similar fashion, now we are not putting our nozzle aligned with the center of mass, but we are putting it offset from the center of mass, so that our, instead of moving forward, our cube satellite rotates toward the direction that we want it to rotate. But this is one class of solution that we can apply in order to achieve attitude control problem. So let us see some examples um, how the direct torque can be applied. One best example is to put the fuel tank and to put the nozzle, and there is combustion of the fuel uh, above nozzle, and the fuel ejects from the nozzle, which provides the force in opposite direction, and that acts as torque to the satellite body. And this picture is of the Apollo service mission that was used in moon mission, but it is for the large mission. This sort of chemical propulsion is also used in small satellite missions. For example, this propulsion unit that was developed by Down Aerospace is 10 mm times 95.4 mm times 95.4 mm. So we can imagine that uh, small modules are also made, but there is one strong disadvantage, that is the propulsion element inside the fuel tank might get finished, and as the satellite itself is a smaller one, there is not chance of putting large amount of propulsive element inside the chemical inside the tank. So the chemical propulsion system are attractive to only larger satellites, but it is not widely used for small satellites. And the propulsion for small satellite is also area of active research interest. And I've included some of the project that I found very interesting while I was researching in this field. And the next type of propulsion system that provides a direct torque is the micropropulsion system. it works. The mechanism on how the micropropulsion system works can be evaluated from this contraption here. So here is a bucket of water and the water is boiling. The steam goes into this ball from these two vent, and there are two nozzles from where the steams eject. And as the nozzles, the point of nozzle is very small, so when the uh, steam eject from here, it ejects from high velocity, and this ball start to rotate in opposite direction. So this is the basic idea behind the fundamental physics that is working behind the micropropulsion system. So what the this author Fui, I think her name was Catherine Fui, and our professor did this project as our final year project. So what they did was they created this nano structure where there is this V-shaped structure that mimics the nozzle here, and they have put small heater, and this is the heater. This small heater is placed on two sides of the nozzle, and here is the water. And when the water reaches this heater, it evaporates and ejects from nozzle, so that this phenomenon is mimicked. And you can see this is a CubeSat 10 centimeter by 10 centimeter by 10 centimeter, and they have created this one module. So they had successfully use these three modules in the CubeSat in order to demonstrate the effect for their thesis. And it was very interesting project. And the drawback of this system is, as always, there is a limit to how much water we can put. But the advantage is that they developed the system so that with less amount of electricity, they could provide reasonable torque in order to move the satellite. So this is one of the interesting recent project that was being done. As you can see, the second version of this project was done by another students of the same research professor with whom the Catherine works, and they actually extended the project of 2017 to their own thesis in 2019, and uh, uh, developed the uh, better version of the project that was done before. And this is one class of propulsion system, and there is another class of propulsion system where the idea behind the provision of torque is same. There is always ejection of some material at high speed, but the way how the material are ejected is different here. And in this system, the propulsive element are ejected by strong electric fields. And I have provided the link to the project that I have taken this image in this slide, which I can share after the talk also. And the man behind this project did all this work single-handedly. So he does in YouTube, he does live videos where after he has manufactured each of these parts, he assembles them with live audience, and he's very interactive. And I think if you are interested in this project, he will be very happy to get in touch with you or to suggest you to the direction that he finds best. So the we finished the class of method that can provide torque, and that we named direct torque. And as already mentioned, this type of systems are not yet fully developed and not are in research phase, and they are not attractive when it comes to setting up in our CubeSat. They are only used for experimental purpose, but they are getting better. But the ones that are already established and widely used in space missions are those which use magnets. So how do the magnet play their role in attitude control system? Let us dive into that. Let us suppose that I have a satellite and I have fixed a permanent magnet in it. So when my satellite is deployed into the orbit, my satellite starts moving in. It rotates around the orbit, but also it rotates around on its own axis. So it is the term is tumbling. So it is moving forward in orbit, also rotating on its own axis. So what happens is that if we put one permanent magnet inside our CubeSat. So the magnetic field of the permanent magnet and the magnetic field of the Earth interacts until the magnet of inside the satellite is aligned with the Earth's magnetic field. So it is very simple and very and the control system that works without any coding or software. You just want to plug a permanent magnet inside your satellite, but there are also some points where we can be clever. So we can align our magnet in such a way that whenever it aligns with Earth's magnetic field, when it is above India, we make sure that we place the camera such a way that the camera will point towards the India. So we can be clever. And I'd also like to mention that the SANOSAT one we that is about to get launched uses this sort of technology. It uses passive magnetic attitude control by using permanent magnet. And for our next satellite, we are working on more advanced type of control system which we are going to discuss now. Now, the disadvantage of this is that the once the magnetic field of our permanent magnet and the magnetic field of our Earth is aligned, then there is no way we can change the orientation of the satellite. It is already locked, but it can still rotate in this axis. So in order to cope up with that problem, what we can do is instead of using permanent magnet, we can use electromagnet. Let's say this is x-axis of our satellite, this was y-axis, and this is z-axis. So what we did is that we put three permanent magnets in our axis. Let's say I activated this magnet along the y-axis. This was north pole, and the south pole of the magnet aligned with the north-south pole of the Earth's magnetic field. So let's say I want all of a sudden I want I want my satellite to rotate around z-axis. So what I will do is I will reverse the polarity of this magnetic field. This will be north and this will be south. So the north and north pole will repel, and this south and south will repel, so that the our CubeSat will move in this direction, and we can actively control the orientation of our satellite. That is why this sort of control system is known as active control system. That is, we have the control over the orientation of our satellite. And this technology also we had experimented, designed, and validated as our finalized project with ORION Space. And this is the technology that we are about to use in our next satellite. So if you are wondering how these magnets are fitted in the satellite itself, then it will look something like this. This will be the magnet for x-axis, for example, and this will be for y-axis, and another coil will be for z-axis. So you might be wondering why there is no coil in this fashion in this rod, because if we put another rod erecting it vertically, then it will take space and we could not stack another PCB above or below it. So we can make your code electromagnet, and it will work equally well. So in this is the way our magnetotorquers are work. And for those who are finding this topic interesting, you must be aware that the topic of our today's talk is not about how those control systems are implemented, but we are only talking about the technology. So there is another problem when it comes to how these magnets are driven so that the active control system is achieved. That is another interesting problem, but that is beyond the scope of today's talk. So by this way, we have talked about the direct torque control of satellite, on which we discussed about propulsive force and the magnetic force. In this magnetic force, the interaction between the Earth and the magnet inside the CubeSat provides the torque necessary for magnet to for satellite to rotate, whereas in propulsive system, the propulsion of element from the satellite itself produces the opposite force, which will be used to provide torque to the satellite. So now we have reached to the second type of way on which we can provide the torque to the satellite. So I think you have already guessed that by using Earth's magnetic field as a source of energy to change the orientation of our satellite, it is almost evident that the torque provided by those systems won't be very large. So there are two things that we need to make sure. One thing is that if we want to use the magnetic control system, then our orbit better be close toward the Earth, because the magnetic field of the Earth is stronger toward inside. As we go inward the Earth, then it is outward. So if our orbit was that of large satellite, then it will then the magnetic field on those area would not be strong enough to move those larger satellites. So this type of magnetic technology is only used in low Earth orbit, that is those orbit which are very near to the Earth. And the CubeSats and PocketSats are usually low Earth orbit satellites, so it is very reasonable technology for cube satellite. But I think most widely used and most effective types of actuators, that type of technology that we can use to rotate our satellite to our desired direction, is known as momentum exchange technology. So what I want you to do is, I want you to imagine a motor where let's say I have fitted a ring. Uh, the ring is manufactured such that it has high moment of inertia, and it is fitted on the motor, and the motor itself is fitted on this plane. And let us imagine that this plane is the one side of the satellite. So what this setup is, that there is a motor and there is a wheel with high moment of inertia, and that is known by the name of reaction wheel, or we also call them flywheel, but in space technology we call it by the name of reaction wheel. And the motor itself is fitted to the satellite body. So what happens is that, let us assume that the motor was at rest, and if we suddenly rotate the motor in this direction, then the satellite body will rotate in opposite direction. That is known as mo, momentum exchange. And the physics behind this phenomenon is that when the both motor and the wheel was at rest, there was zero momentum, and when we rotated this wheel suddenly in one direction, the momentum was created in this system. So we already know that in a closed system, uh, the momentum is always conserved. So we had zero momentum to start with. So in order to conserve the momentum that was created by this reaction wheel, the satellite body will itself rotate in the opposite direction. So this is how we can move the satellite body, and this is very effective one. So the rate of change of angular momentum gives us the torque, and this is how we generate the torque in order to move our satellite. So uh, this is the setup that we work with in Orion Space. And actually I was about to put one video for the demonstration of moment reaction wheel control system. So uh, I think it will be lengthy if I start short for the video in my laptop now, but I will mail it later so that you can look at it. So how this work is that, here is a spherical ear bearing. So we put a ear inside here. There is one opening on the other side. So when we put the compressed air inside it, this transparent ball floats in the air, because this structure provides, there is hole in this structure, and the compressed air that we feed from this point are equally distributed from this hole, and this lifts this transparent plastic. So what happens is that we have simulated the low friction environment of the Earth, and inside this mock-up satellite we put the reaction wheel and motor, which are actually like this. And what we do is, we we command this satellite to point it certain direction, and we rotate this reaction will in such a way that our desire the orientation of our satellite matches the desired orientation of our design. the desired orientation that we want to gain. So, but this in this system we only talked about one reaction wheel, and it will move the satellite in only one axis, about the axis of this reaction wheel. But we can equally attach three reaction wheels, three sets of reaction wheel in our satellite. So it will be better if you imagine this picture in this way. So here is one reaction wheel in this axis, here is another reaction wheel, and here is another reaction wheel. So what you do is, if you want to move your satellite in this direction, you rotate this reaction wheel. If you want to move this satellite in, I'll make the coordinate axis x, y, z. So based on uh, about which coordinate axis you want to rotate your satellite, you move the reaction wheel about on that axis. So again, there is one question here: what is the mathematics, what is the physics, or what is the system that determines how to move our satellite based on the view of control theory? So as I have already mentioned, this is wide topic, and that will not be covered, but I mentioned this to let you know that control theory is extensively used in this system. So if you are interested in robotics or control theory, this attitude control system of satellite might be the best thing for you. So, and what we talked about now is this reaction wheel, and how it works is that it creates the change in angular momentum, and in order to conserve that angular momentum, our satellite body moves so that we can achieve our desired orientation. That was the logic behind it. And the main principal point behind this reaction wheel is that our reaction wheel was always fixed on the satellite body. As you can see, reaction wheel on this axis is fixed here, on this axis is fixed here, and on this axis is fixed on the this side perpendicular to the plane A, along the plane of our laptop. So there is another way you can play with reaction wheel and create the rotation of satellite. So you can assume this man to be satellite. Suppose that this man is satellite, and you want to rotate this man as he is doing in this uh, picture. So what you will do is, you will rotate this reaction wheel in one speed, but instead of changing the speed of reaction wheel and creating the change in angular momentum, what you do is you rotate the reaction wheel, so that whenever you rotate the reaction wheel, and for refresher, I would like to mention that whenever one wheel is rotating in the axis, the angular momentum is perpendicular to the axis that is given by the right hand rule. So in this diagram, if I wrap my right hand around this, the direction of this motion, the arrow will point downward. So the angular momentum of this wheel is downward. So what this man is doing is that he is rotating a reaction wheel, and he changing the direction of angular momentum, because while he was pointing upward, the angular momentum was pointing up, and when he moved the wheel below, then the angular momentum now is moving pointing downward. So in order to conserve this angular momentum, what is happening is that his body is moving so that the complete angular momentum of the system is conserved. So that is the principle behind the control moment gyro. If I made you confused, then you just need to uh, uh, keep two things in mind. In reaction wheel, it is the reaction wheel that accelerates and deaccelerates, and that acceleration or deacceleration creates the change in angular momentum. And in order to conserve the angular momentum, the body of satellite moves, because the body of satellite is fixed with the motor. But in case of control moment gyro, we can rotate the reaction wheel, but the motor on which the reaction wheel is fixed itself can be rotated. So it can be demonstrated by this figure. So here is, I found this project by, so actually in ORION space we will be working with reaction wheel, because control moment gyros have elaborate mechanism that is very hard to fit inside a CubeSat. So, but I found this project by Prabhakaran, named Adaptive Singularity Free Control Moment Gyro, that he did in 2020. And what I liked most about this project was is fabrication of the control moment gyro, because if you look in the internet, the mechanism of control movement gyro is very elaborate, and at the first look it already looks, oh, this is a complex thing, but this mechanism is, I think, the best one in my view, in my eye. So I thought I'll better share it with you. So uh, by taking analogy of this man, what we can see is here is a reaction wheel and here is a motor, and this motor can rotate this reaction wheel. If it were a reaction wheel based control system, then this will be our satellite body and it will be done. But it is control moment gyro. So what is happening is that as this axis can be changed in control moment gyro as this man does it with his hand. In this case also, the axis about which the reaction wheel is rotating can be changed by another motor which is below. So whenever this the motor below rotates, the angular momentum which is pointing toward this direction right now, let's say point toward this direction, and in order to conserve that angular momentum, the whole body of satellite moves because this motor is fixed in the satellite body. So this is the control moment gyro, and this is the figure that is sort of schematic for this. And if you are interested in, since I had already cited this book, I'll also like to mention that this book by Hans-Peter Schwab is very nice book for understanding the mathematics behind this reaction wheel and control moment gyro. So if you are interested, you can just take a screenshot and look for this book. And and this is all regarding the control moment gyro, but there is another great project by TensorTech, and TensorTech are the company that are based on Taiwan, and we, as ORION Space, we talk with them constantly, and we take their advice and we consult them regarding the attitude control system, but because they are already established in this field, and with their permission, I included this photo for that they call reaction sphere. So as you can see, in above examples, you need three motors to control three axes of satellites, and you need such three motors to control three axes. But they have created this reaction sphere where inside here is a ball, sphere ball, which interacts with the coil, electromagnetic coil they have made around here, and with this single mechanism they can provide the 3 degree of freedom. So it is very interesting technology, and the working principle behind this technology is this control moment gyro. Although at first sight here is a sphere and the sphere is rotating, it do not looks like it is control moment gyro, but if we see its design in detail, and if we were to mathematically model it, then we'll use the mathematics behind the control moment gyro. And finally, we have talked a lot about the theory, and if we were to ask what sort of reaction wheels are actually used in the space, then these two images will demonstrate the size and scope of the project very beautifully, because in the International Space Station you can see that the size of the reaction wheel is comparable to the size of man. And one advantage of reaction wheel is that you only need electricity, you don't need propulsion system, etc. And there is no way that fuel will be finished because the reaction wheel works on electricity. And reaction wheel can be as large as a man and as small as 10 centimeter by 10 centimeter by 10 centimeter cube. So this is a project of large satellite, and this is for cube satellites. Finally, I have come to the point where I wanted to share mathematical motivations behind the things that we talk, because if we were to divide the thing that we discussed, we talked that we are doing attitude control system, and there are two ways to achieve the torque to move our satellite. One is by direct torque that can be either done by propulsion or either by utilizing Earth's magnetic field. And there is another class of technique that you can use, that is by using the change of angular momentum. So, but the time is already 8:45 years, so I think we started a little bit late. So I like to ask if I think there is only 2 or 3 slides, and if it is late, we can stop here. But if you like, uh, if you will want to get mathematical intuition and motivation behind the thing that we just discussed, then I can go further also. Then, what will you suggest?
We can continue. We can continue with the further
Yeah,
slides.
thank you. And personally, my interests are also mathematical modeling. Even though I am a student of communication, electronics and communication engineering, I always loved physics and mathematics, and I think this is common, mainly common for the people who are in their 12th grade or in their bachelor's, because mathematics seems to be a very interesting topic. But then sometimes there is also a problem because that that I personally faced was like I was very interested in mathematics, but I did not know mathematics, and I did not know where to start from and things like that. So that is the problem that can be related with the guidance. So because if the teachers are good, then the students are good and things like that. So uh, there are many factors, not only teacher. I'm not trying to blame teachers, but uh, getting proper type of friends and being in the environment where mathematics is appreciated and those sort of things are, I think, very valuable for those who love mathematics, because there might, due to uh, little time that is provided, and the content of the course that we need to cover, so it might not be possible for teacher to go in every details of every type of mathematical topic that is presented in our course. But the point is, if any of us are interested in that sort of things, and the slides beyond this point is, I think, for will be interesting for them. But saying that, the thing that we are going to talk is not complex, but I think will be interesting for many of us. So what let us go forward with a goal in our mind. What I'm going to do now is I'm going to illustrate how these two types of t- techniques that we discussed, one direct torque based and another is momentum exchange based. So mathematically, how we can realize these two techniques, and that I'm going to discuss now. So before we go anywhere further, first of all, I like to remind the fundamental equation of translational motion, that is F equal to ma. So basically what this equation says is that if you ever want to accelerate your object, you better provide force to that system, to that object. So let us suppose this table is at rest, and this child wants this table in this point. So mathematical, so in terms of physics, what he is trying to do is he is trying to move this table here. So the table at rest needs to be at motion. So let us say rest velocity is v0 and it is v1. So the velocity is increased, so there is presence of acceleration. So whenever you are trying to alter the state of motion of any object, you need to provide the force. So altering the state of motion can be known by the name acceleration. So whenever, let's say, if a car is moving in a certain constant velocity and you want to stop it, then you need to apply force. That might be as brake, or if it is at rest, you need to apply force. So whenever you want to change the state of motion in translational dynamics, you provide force. So in the same way, since we are talking about rotation in this satellite technology, this F equal to ma does not work as it is. So we need to look for the rotational counterpart of the F equal to ma, which is tau equals to I omega. I think many of us have already studied it, and it can be understood analog to F equal to ma. And m in rotational dynamics, mass is replaced by moment of inertia, which parameterize how mass is distributed along some axis, and acceleration is replaced by angular acceleration. that is also denoted by alpha, and force is tau. So whenever we are talking about rotational dynamics, we talk about tau equals to I omega dot. But there is one problem in this equation here, because we do not use this equation as it is if we were to understand the rotation of satellite. Why would we don't use this equation is that every terms that we let us say this is the satellite and it has the moment of inertia I, and its angular acceleration rate of angle is omega dot. So I think every one of us had came up across this formula once in their career as a student. But what I'm going to point out is that this I and omega dot that we used in this formula was the vectors that was viewed from one reference frame. That is not the body. So it might seem little bit confusing at first, but uh, all I want to point out is that torque is a vector, omega dot is a vector. So we are talking about this sort of line vector. But whenever we are talking about vector, we must, it is already assumed that there is some coordinate system, because if you were to define a vector, you write vectors in 3 numbers that defines the point from x-axis, y-axis, and z-axis, and the vector is defined in that way in three-dimensional world. So whenever we talk about a vector, one coordinate frame automatically comes into the action. So this might be thing that you have thought about or not, but it is actually there. Whenever we are talking about vector, we have a coordinate frame. So the problem is that whenever we used this equation, all those parameters were the vectors that was seen from the coordinate frame that was not inside the body. So this I and omega dot was those vectors as observed from the outer reference frame. So it could be the earth or anything. So what is the problem there is that if let's say this satellite rotate and it came in this orientation, now the moment of inertia changes as seen from this reference frame, because moment of inertia is something that parameterize the distribution of mass about some coordinate axis. So since the mass has moved from this orientation to this orientation, the I also changes, omega dot also changes. So there is no way we can know what is the moment of inertia of our system. It is like saying that whenever you move from one point to another point, your mass is changing. So you'll never be able to say that your mass is x kg. In place of mass, you replace the word moment of inertia and visualize it. So if you can't say that the moment of inertia of your satellite is this much, then you never know what value to put in the mathematics whenever you use the value moment of inertia. So this was the problem. The problem was that all the physical parameters was that observed from the reference frame, not inside the satellite itself. So in order to, this problem was solved by Wheeler. He was great mathematician, and I think physicist too. So what he did was, instead of formulating this equation, everything from the reference frame outside of the object, what he did was he constructed the body frame, and the body frame was constructed in such a way that whenever the satellite moves in new orientation, the body frame moves with the satellite. So now instead of looking this I from this inertial frame, you can look this I from body frame, and the I will never change, because body frame is moving with the satellite, and from the eye of those frame, the moment of inertia of the satellite is always same. So if we introduce the body frame, and if we formulate the problem such that the moment of inertia and angular velocities are those as observed from the body frame, then you get the equation known by the name of Wheeler's equation of rotational dynamics. So the derivation of this formula is done in Wikipedia, and you can find it in any book of classical mechanics. But the interesting and beautiful part of this equation is that if you look at this equation, you find that I omega dot, that is rate of change of angular velocity, is determined by two factors. One is tau, that is torque applied to the object, and another is I there is omega times I times I omega, and we know that this I omega is momentum L. I think the momentum is denoted by L equals to I omega. So what we can see that is that whenever we formulate the equation of rotational dynamics by introducing the body frame, we come across the two terms, and initially there was only one term. So if you want to change the direction of satellite, you just apply torque. But from the view of Euler's equation, we get two terms, and it is, now we can see that it is not only the torque that can be used to rotate the satellite, but it can also be rotated by altering the angular momentum. So that is where this uh, second type of problem, momentum exchange, came in. And you can see that this torque, this part of the equation uh, is the first type of problem that we encountered that we named direct torque problem, and this denotes the second type of problem that we named as momentum exchange problem. So Euler's equation, this part denotes the momentum exchange part, this denotes the direct torque part. So whenever, let's say you are mathematically modeling your satellite and you found that whenever you fire the thruster in your satellite, the amount of torque is this much. Then you put that amount of torque in this value and you simulate this equation, and you will find how your satellite will behave. Or let's say if you put a reaction wheel in your satellite and you want to simulate the behavior of the reaction wheel in your satellite, then what you do is that you find the angular momentum of a reaction wheel and you put in this part of the equation, and your reaction wheel is simulated. So this is how the whole content of our talk fits into a nice equation, and I think this is the part where I like to stop my talk. And if you had any troubles or any problem regarding the content of the talk, or any questions that you would like to ask me, then I think I'll be very happy to take those questions. Thank you.
Thank you so much, and indeed it was very insightful. So our audience have many queries and they are very eager to ask them. So it would be great if you help them out. Um, they can raise their hand if they have queries. We will unmute.
And I think there are two parts that I had not been ready. I was supposed to show a video, and I had some.
Okay.
I think
Sorry.
I should
No, you can continue and
forward.
we can take the questions later. No issues.
Uh, if you have question, you can keep on asking them, and in that meantime, I'll open one video to demonstrate how the reaction will work.
Okay.
And Mr. Rakesh Chandra Prajapati, who is CEO of ORION Space, is also present in this talk. So I think you need not, if you are asking question, you need not constrain the question in to the attitude control system only. So if you have any question regarding the space technology, or uh, space policies, or space laws, or those sort of things, also I think you can feel free to ask those questions.
Okay, sure.
Hello, sir.
Hello?
I have a doubt
Yes, please.
regarding the chemical propulsion. I wanted one information.
Um, uh, it's very hard to hear you. I think it is due to internet connection or something.
Yeah. So may I get your mail ID for further information because it
Oh,
was
yeah, yeah,
late.
sure, we can do it. I'll put the mail ID of Orion Space in this chat group, so you can reach us anytime you
Yeah,
like.
sure, sure.
And not only for questions, if you want to get involved in project, or if you have any interesting thing that you, or interesting suggestion that you would like to suggest also, we are free for those suggestions.
Thank you so much, sir.
uh, this is the Gmail address of Orion Space, so you can mail us.
Thank you so much, sir.
You're welcome. Thank you. uh, there's one video that I think will be interesting. Can you see my screen?
Yes, yes, we can.
Is there a video in the screen, or what are you seeing in my screen? Because they are in two different tabs, and I'm not sure what is being shown. Is there a video?
Yes,
Yeah.
about final notes at.
Oh, yeah, yeah. And so I'll give a small description of this video, and you can see it. So uh, the setup that I described earlier is this one. So below is the spherical air bearing, which by the help of compressed air we float the platform, and the satellite experience low friction like that of the space. So what we are trying to do is we are trying to move the satellite in the desired orientation. So first of all, we are giving it 45 degrees of command. I think so. So you can, for reference, you can assume that the of blue colored computer, that is microcontroller, blue colored rectangle is facing toward us. So that is 0 degree, and we are giving command to move it in 45 degree. So as you can see, it has moved 45 degrees, and again we command it to go to 90 degrees. Now you can see that the rectangle, this line is now perpendicular to how it was initially, so it is also now in its 90 degree. But I think you can already see that the sort of problem that was just demonstrated in this video was single axis problem, because if we are about to put this system in the satellite, then our system could only move around one axis. So three such reaction would give us complete degree of freedom about all three axes, and we could move our satellite to any direction that we want to move. So that was the video that I wanted to say. Thank you.
Thank you so much. Now we can have queries of the people. They can raise their hand. Okay, so there is no questions at all. So with this, I would like to extend thanks to Rakesh Chandra Prajapati, CEO of ORION Space, Jatin Thapa, Research and Development Engineer, and also you, Rishabh Manish Sharma. Thank you so much. It was amazing time to spend with you. Thank you for coming. This event wouldn't have been the same without you. Thank you so much.
Thank you.